Hello, welcome to the lecture series on vehicle dynamics. In this session, let us discuss about steering system models. The steering system shown here, it can be modeled to determine steering torque required for steering the road wheels at a given vehicle speed. What I mean by that is, if you consider these wheels, here at the road contact point, there is vertical load acting, there is lateral load acting, also there is a traction force acting. Okay. In addition to that, there are many moments. Moment about vertical axis, moment about x-axis, moment about y-axis. These things are all acting. So on both the wheels, you have these kind of forces, as well as moments. Now the question is, I want to steer these wheels left or right. So now the question is, at the steering wheel, how much torque is required? At different vehicle speeds. This, if I can estimate as a driver, how much torque I can impart, and if additional torque required, what assist I should use so that the torque can be supplied and the wheel can be steered. That is the whole thing. So let us model this now. As I mentioned, the ground reactions on the tire are described by three forces and moments. The forces are normal force, tractive force, lateral force. The moments are aligning torque, or you can say aligning moment. Aligning moment, I can say that. Rolling resistance moment, overturning moment. On front wheel drive cars, an additional moment is imposed by the drive torque. So I have shown a loaded tire. It's a ground surface. This is the contact patch. This is the traction force. You know how to calculate traction force now. The lateral force, the normal force. You know how to calculate each one of them very well. So these are all the forces. And this is the tire axis passing through the center. About the z-axis, there is aligning moment. Already I explained about aligning moment. Whenever you are taking a turn, at the end of the turn, how the wheel comes back because of the caster angle provided. So we have studied already about this. Okay. Now there is rolling resistance. Suppose this is the direction in which the wheel is rolling. the rolling resistance will be acting opposite. This rolling resistance about y-axis, it will create a rolling resistance moment. Similarly, there will be overturning moment about x-axis like this. If there is unevenness, it will be overturning moment. In addition to that, whenever the tire rolls taking a turn because of the lateral force, a tire slip angle coming into picture, either will provide a negative camber or a positive camber angle, so depending on the design. So there is caster angle mu, there is camber angle, there is alpha, that is nothing but wheel slip angle. Of course, steering axis inclination angle you will have. So all this. Now I have shown all these forces at the tie rod interface here. You can see the vertical force acting here. This is the traction force acting. There is a lateral force acting over here. Okay. About z axis, you have aligning torque. About y axis, you are having rolling resistance moment. About x axis, you are having overturning moment. Yes. The wheel is spinning on tire axis, that is spin axis. That is a wheel torque that is acting. As I said, this is the tire slip angle. Then you have the camber, correct? Okay, here positive. Okay, camber angle shown here, that is gamma. Okay, fine. When all these forces are there, now let us see how to find out the equations for aligning torque, rolling resistance moment, overturning moment, net vertical force, net lateral force, net traction force, all these kind of things, and what is the moment it is going to create. You see here, our steer axis is here. And the forces are acting here. And these forces about this line create moments. Suppose if I have a vertical force, correct? Then probably you see here, this is the vertical line. Then resolve this way and this way. Then about this force if I take, and then the distance if I know, so I can find the moment, correct? That is the way we can find the moments and other things. So all these forces are acting over here. Your steering axis line is at a distance d from the center line of the tire. This d is known as scrub radius, and this angle lambda is known as kingpin inclination angle or steering axis inclination, SAI. Of course, it's a front wheel driven, and the half shafts will be making an angle zeta with the horizontal line. Okay, and r is the radius of the tire. Okay, total moment. Now please remember these angles. Nu is the caster angle, delta is the road steer angle, lambda is kingpin inclination angle, T lateral offset at the ground, what you can call it as the scrub radius. FZL, if I write vertical force on the left wheel, vertical force on the right wheel. Okay, right, sir. Let us find the moment due to these vertical forces. Moment due to vertical forces is given by this equation. So how do we get this equation? Probably now you see it's taken from one of the Gillespie's book. So you can see here vertical force considering steering axis inclination, then vertical force considering nu, that is caster angle, you'll get this. Finally the total vertical force will be this. Moment due to vertical force will be this. So I suggest you to study this geometry, and after resolving all these forces, take the moment about the steering axis and you will get this equation. Similarly, moment arising from lateral force. Okay, now you look at these slides and you can get the moment due to lateral force. Again, if you look at moment due to traction force, okay, traction force, you will be getting from here. Okay, study the geometry, that's fine. Then aligning torque, right, from this. So these equations have to be written looking at the geometry. So that's how the rolling resistance and overturning moment, their second order effects means they are negligible, so we are neglect. So the contribution is negligible, we can ignore that. Okay, once we have got these forces, now let us look at steering torque variation. The steering moment due to vertical loads. Considering only steering axis inclination, here steering angle, I am going to vary the values of delta. I maintain a scrub radius or offset as 1 inch, and the lambda value, that is steering axis inclination angle, is 10 degree. So for this vehicle it is 10 degree. D is 1 inch. Left wheel load is 800 pounds. Right wheel load is 600 pounds. If I go on giving different values for delta on the steering torque, if you see, okay, one for the left, one for the right you get, and the total one is this. So suppose steering angle 15 degree, Then the steering torque, so inch pound. So it can also be converted into Newton meter like this in the counterclockwise direction. Minus 15 degree, if you draw it, okay, vertical line, maybe somewhere here you are going to get, okay, this is the value of the torque. So same way for the second part, vertical loads again, caster angle. Delta values are varied here. So 5 degree caster angle is here, D 1 inch, one is left, one is 800 pound, right on it. So individual wheels we can, steering torque you can calculate, and combined steering torque we can find out, total steering torque. Correct? This is not very significant. Okay, very significant. But with steering axis inclination angle, this is quite significant. So I just done some simulation in Newton meter, what is the steering torque required for different caster angles. So moment about steering axis due to drive line torque. This is a drive line torque. So the moment you are going to get is this equation, and zeta is this angle. Okay, so now says that the lateral inclination and caster are small enough that the cosine function can be assumed unity. Hence, this part you can leave it, and the equation can be written like this. So here also, right, you can see what is the moment you can find out. Right, now the total T total, a steering torque total. So vertical forces, lateral forces, traction, aligning, drive line. Wheel is also rotating about Z axis. Correct? No? So then you can simply say delta Z. This is your wheel dynamics. No. So yeah. When you are doing delta, it's about that point. You are rotating, right? Fine. Wheel inertia about SA axis and tire damping. Okay. So this is considered over here. Next is considering, here we are not considered the wheel inertia, or considered wheel inertia. Now you know this, 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 and total I have written down, added everything. And one more thing here, the lateral force I have written it as, okay, tire stiffness, or you call it as cornering stiffness of tire. So lateral force divided by tire slip angle will give you C alpha. So these lateral forces I have replaced by this. Okay. And you know FXL, that is nothing but mu. So I have brought the road friction into picture here. Yes, sir. After considering all this, I have written over here. Let us look at this. Depending on the conditions, this will vary. For a given vehicle D is fixed, lambda is known, vertical loads vary, yeah, anyway, caster angle, then wheel cornering stiffness we know, okay, angles we know, tie radius you know, new, that is your caster angle. So all these values are known. Now it is possible, if I know all these values, for given as we vary the value of delta, what is the torque required we can find out. What if the delta values varied, what is the torque required we can find out. So again here you can say torque, and for different values of delta, if you know all these parameters, we can draw the torque curve versus delta. So again, delta is equal to 57.3 L by R plus K V squared by GR. Let me write. If you know the vehicle speed, you know the understeer gradient. For the vehicle speed, we can always find out what is the delta required. Okay, vehicle speed, if you know, we can calculate delta. Delta, if you know, we can find torque. Correct. That's what this model is going to help us. Anyway, let me add some more terms here. Whatever I have calculated is the torque, that is about steering axis, correct now? Then here, what is the force at this point? Correct, force on this, if you consider this is inner end is outer end of the tie rod, this total plus this is steering arm dynamics, because this fellow rotates like this, so this is steering arm dynamics. So total torque divided by steering arm length, I'll get this force here. Then what is the force at the rack? The force on tie rod plus this dynamics, tie rod dynamics, that I have considered. Then finally, what is the here on the pinion? I have considered this force plus I have considered this dynamics, linear dynamics. Okay, finally, what is the torque here? Force on the pinion and R pinion, anyway, that is a torque. Then I have considered pinion dynamics. Okay, that is the torque. Okay. If I am using any gear, ratios or whatever it is, I'm dividing. And that total final must be hand wheel torque plus motor torque. Okay, the idea is now simple. First, I can say delta is equal to 57.3 L by R plus K A by BG, lateral acceleration, or we can say V squared by R. I know understeer gradient of the vehicle if is known. So turning radius is known. Y value if I know, V value if I know, I can find delta. So that is delta versus torque if I can get it. So from here I can get the total torque. Out of the total torque, if I subtract driver's torque, the remaining torque should be given by the assist. Correct? No? If I use electrical motor, that motor should develop the remaining torque. Okay, that's the idea behind this. Okay, this torque plus assist motor torque should go flow here. So how exactly assist motor torque will be controlled? There is a controller. Give the vehicle speed to the ECU. Steering angle delta, as I said, delta, vehicle speed V, ECU based on the model will calculate the torque required. Out of this torque, whatever torque is given by the driver is also given. Subtract that remaining torque, make it to flow to the motor. That means adjust the current value of the motor, because torque versus current characteristic for the motor is available. From that what should be the torque, it will decide. If you have a characteristic, whatever it is, characteristic is there, and if there is a gear system, further torque gets multiplied and it will flow to this point. Okay, again it will get the feedback from here, right? From shaft itself, it will be getting the feedback. So to do the simulations, probably we need all this data in the correct units. Then we can rewrite the model equation. Then we can draw the Simulink diagram for that. Correct. Then we can plot T versus delta for different vehicle speeds. Correct. T versus delta for different vehicle speeds. So this is what we should feed it to the ECU. So ECU comes to know what is the vehicle speed, and also if it comes to know the delta value, delta vehicle speed 80, and then it will decide this should be the torque. That's how we can do this. So simulate this, create a lookup table and feed it to the ECU system. ECU will control the current to the assist motor so that the torque requirement can be satisfied. So now you can use MATLAB tool, you can simulate and After simulating some of these things, probably on a microcontroller, you can port the code and test. Okay, right. So that is about modeling of the steering system. Thank you.